Let us start today's class. In today's class, we will continue with asynchronous counter. In the previous lecture, we designed all asynchronous counters using D flip-flop. This is the example of a 2-bit asynchronous counter that was shown in the previous lecture. Now, we need to know what was the strategy followed for designing asynchronous counter using D flip-flop. What we did, actually, we made our D flip-flop a toggling circuit. The output was taken from Q prime and it is fed to the D input. So what happens in every clock pulse triggering, first one output is fed, then when Q0 becomes 1, then 0 output is fed. So every clock pulse triggering, we get the toggling output using this D flip-flop. Similar thing happens for the second flip-flop, but for the second flip-flop, the clock pulse is taken from the Q prime output of the previous flip-flop. That means main strategy to make this type of counters is to have the toggling operation in each flip-flop mode. Now things are a bit easier if the designings are done using JK flip-flop or T flip-flop. In JK flip-flop and T flip-flop, we can have this type of toggling operation without taking feedback from the output side. Let's design this type of asynchronous counters using JK flip-flop. We know for JK flip-flop, if both the inputs J and K are fed by one input, 1 and 1, in every clock pulse triggering, the output Q toggles. So this toggling operation of JK flip-flop is utilized for designing asynchronous counters using JK flip-flop, where J and K, both the inputs are fed by constant input 1. This is the example of 2-bit asynchronous counter using JK flip-flop. The designing is similar to the case that we used for D flip-flop, except inside this JK flip-flop no feedback is taken. So all the JK flip-flops are fed with high input, 1 1 input, 1 1 input, and the output Q0 prime of first flip-flop is taken as the clock pulse input of the second flip-flop. The operation is similar to the operation of that was shown for D flip-flop case. Here in each clock pulse triggering, the outputs will be toggled. When the output of the first flip-flop toggles, then every negative triggering of this Q0, the output of second flip-flop, that is Q1, will be toggled. In this way, we'll keep getting the asynchronous counting operation. Now, if we want to increase this asynchronous counter to 3-bit, what we need to do, we need to add another flip-flop here with similar format. This is the example of 3-bit asynchronous counter using JK flip-flop. The operation is similar to the one that was shown in the previous slides. Here we need to remember that this is the LSB and this is MSB. That means Q0 is the least significant bit and Q2 is the most significant bit for this 3-bit asynchronous counter. Now I hope all of you will be able to design this type of asynchronous counter using T flip-flop and RS flip-flop. The main strategy is to operate all the flip-flops in toggling mode. In this flip-flop operation, the outputs are taken from Q0, Q1 and Q2 and it's acting as up counter. What does up counter mean? That means it will start from 0 0 0 and in this way it will go up 0 0 1 0 1 0 0 1 1. In this way it will have the up counting. What if we need to design the down counting? What does down counting mean? Down counting means it will start from 1 1 1 1 1 0, then in this way it will come in descending order. So how to do that? The down counting operation is very simple. Instead of taking outputs from Q0, Q1 and Q2, we need to take the outputs from Q0 prime, Q1 prime and Q2 prime. Then it will act as down counter. If we see the output table, then things will be more clear. This table shows the output Q0, Q1 and Q2 for the counter that was shown in the previous slide for each clock pulse triggering. At the very initial moment, the outputs were 0, 0, 0, Q0, Q1, Q2 output was 0, 0, 0. Then in the first clock pulse triggering, it becomes 0, 0, 1. And in this way, it goes up to 1, 1, 1 and comes back to 0, 0, 0 again. That means in the 8th clock pulse triggering, it recycles. So when we have 0, 0, 0 output at Q0, Q1 and Q2, the Q0 bar, Q1 bar and Q2 bar will give us 1, 1, 1. In this way, we'll get the inverted output in Q0 bar, Q1 bar and Q2 bar. So we can see it will start from 1, 1, 1, then it will go to 1, 1, 0, 1, 0, 1. In this way, it will count up to 0, 0, 0. Then again, at the 8th clock pulse triggering, it recycles. So we are having down counting operation at Q0 bar, Q1 bar and Q2 bar output. So the same flip-flop can be used as up counter and down counters by taking the output from two different sides. Next, we will see how to increase the number of digits in decade counter. The decade counter is widely used counter and very essential counter for a lot of applications. This is the block diagram for BCD counter or decade counter. I hope by now you have enough knowledge to design the circuit diagram that is inside this box. On every clock pulse triggering, the counter will count. It will start from 0, 0, 0, 0, then 0, 0, 0, 1, then 0, 0, 1, 0, and it will go up to 1, 0, 0, 1. When it goes to the next value, it recycles. That means it comes back to 0, 0, 0, 0 again. So it will start counting from decimal value of 0 up to 9. After 9, it again comes back to 0. So in this way, it keeps counting. If we want to see the output in 7-segment display, what we need to do, we need to connect a BCD to 7-segment decoder here, then 7-segment display here. It will show the counting operation using the conventional number we understand. So it will show 0 first, then 1, 2, 3, 4 up to 9. What will be the procedure if we want to make a BCD counter that will count starting from 0, 0 up to 99? That means it will start from 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So after 9, this BCD counter will become 0. Another BCD counter will give me 1 in the most significant bit. So having 1 in the most significant bit, if we have 0, 1, 2 again, so it will show 10, 11, 12. In this way, it will count up to 99. So how to increase the number of digits in decade counter? Let's see the operation. This is the block diagram for 3-decade decimal BCD counter. In each block, we have a single digit BCD counter or 4-bit BCD counter. The circuit diagram inside this box is known to us. Here, if we want to increase the number of digits, what we need to do, we need to connect similar type of counters in series. So this is the least significant digit and this is the most significant digit. And the clock pulse of every BCD counter is connected from the most significant bit of the preceding BCD counter, except the first one. The first one is fed from the external clock pulse signal. But the clock pulse of the second BCD counter is connected from the most significant bit of the first BCD counter, and the clock pulse of the third BCD counter is connected from the most significant bit of the second BCD counter. How it operates, in order to understand that, we need to see the timeline diagram. Let's see the timeline diagram. This is the timeline diagram for single block BCD counter that was shown in the previous slide. We can see the counter starts counting from 0, 0, 0, 0, 0, 0, 0, 1. In this way, it reaches up to 1, 0, 0, 1. Then again comes back to 0, 0, 0, 0 condition. Now, if we see the characteristics of most significant bit, we can see it goes from 1 to 0 after the 1001 condition. Again Q3 starts from 0 and it continues like this way. Again after 1001, which is equivalent to 9, after that value we get 0000. Now if this Q3, which is the most significant bit of any decade counter block, acts as the clock pulse for the next decade counter, then when this Q3 comes back from 1 to 0, the next clock pulse gets the triggering. So when the first decade counter goes from 9 to 0, then it gives a triggering to the next decade counter. So it starts from 0000, but in the preceding side we have 1 because it has got its first triggering. Now if we see this BCD counter, it will start from 0000, then it will reach up to 1001. When this Q3 comes back from 1 to 0, again it becomes 0000, giving a trigger to the next BCD counter. So when it gets triggering, the output starts from 0000 and the next output by the second BCD counter gives us 0001. When we have 1 here, having 1 here, we'll get again 0, 1, 2, 3. It will look like it's 10, 11, 12, 13, 14, 15, 16. In this way, when this output again goes from 9 to 0, it will give another triggering that will make the output 2. So again it will start from 0, 1, 2, 3, 4. As we have 2 at the preceding, it will look like 20, 21, 22. In this way it will keep counting. In this way, whenever it will reach up to 9, then after 9 it will go back to 0, giving a clock pulse triggering, making the third BCD counter output equivalent to 1. So it will look like 100, that means 100, 101. In this way, this 3-decade decimal BCD counter can count up to 999. After 999, all the outputs will go back to 000 condition. In this way, we can increase the number of digits by adding BCD counters in series. Now let us see one of the applications of counters. We'll see how can we design a digital clock using counters. This is one of the applications of counters. In digital clock, there is hour digits, then minute digits, then second digits. Now if we analyze each of the block for seconds, minutes and hours, we'll be able to get the idea how should we proceed for the designing. Let's start from the seconds part. If the very initial clock pulse is sent 1 Hz frequency, then every change that will occur here will be after 1 second. So after every second, this value will be changed, which we want. Now the seconds digit will start from 00 and it will reach up to 59. After 59, it will again come back to 000. So after every 60 seconds, we need to get the minutes triggering. After every 60 minutes, we need to get the hour triggering. So let's start from the seconds part. This digit will start from 0 and will reach up to 9. When it goes from 9 to 0 again, the most significant bit will give a triggering to this digit, making it 1. When it is 1, again it will start from 0, 1, 2. So it will look like 10, 11, 12, 13, 14, 15, 16 up to 19. Then when it recycles from 9 to 0, the most significant bit will give the second triggering that will make it 2. Now we need to design a counter that will count from 0 to 5. So after every transition from 9 to 0, there will be triggering and it will keep counting. So when it reaches to 5, again it will come back to 0. Then the most significant bit will give us 1 signal here, that is the minute. So 1 minute 00 second, 1 minute 01 second. In this way, once it reaches to 59, when it moves from 59 to 00, that means 5 to 0, it will give 1 triggering to the minute portion. and again it will continue like this way, similar to the second circuit. Similarly, we need to design the counter for hours where all the data will be updated after every clock pulse triggering, which is having 1 Hz clock pulse frequency. That means after every second, this second digit will be changed in this way. After every 60 seconds, this minute digit will be changed. After every 60 minutes, this hour digit will be changed. This will be a task for all of you to design this type of clock using the knowledge on the counters that you gained in the previous lectures. This is the complete block diagram that we discussed in the previous slide. 1 Hz clock pulse source is fed through the very initial BCD counter. This counter will count 10 division, that means starting from 0 to 9. This counter will count 6 division, that means starting from 0 to 5. Again, this counter will count 10 division. This counter will count 6 division starting from 0 to 5, and there is a control unit to control our digits. With every counter, we have BCD to 7 segment display in order to see the output in our normal decimal values. Each blocks are to be designed separately in order to get this final output. Once you are done with this designing, you are asked to verify your designing using Proteus software. Let us see another application of counters, that is parallel to serial data conversion. Before we start this topic, we need to understand what is parallel data and what is serial data. In parallel data transmission, multiple bits are sent simultaneously through different wires or channels. But in serial data transmission, the data is sent 1 bit at a time sequentially. We can see we have 8-bit parallel data, that is input data. Now, if we want to convert it to serial data, instead of using 8 lines, we can use only 1 line. In this output, on each clock pulse triggering, each bit data will be transferred. So, we have D0, D1, D2, D3, D4, D5, D6, D7, and we need to send the data through this single line serially on each clock pulse triggering. How this is done? In order to do that, we have used one sequential circuit and another combinational circuit. The combinational circuit that we used, you already have the idea on that, that is the mux. Here we have used 8 into 1 mux. What is the function? In mux, we have data select option and inputs and one single output. This 3-bit data selection option will give us opportunity to send 8-bit data through one single line. If 000 is selected, then D0 will be transferred through this line. If 001 is selected, then D1 will be transferred through this line. If 010 is selected, then D2 will be transferred. In this way, if 111 is selected, then this D7 will be transferred through this line. I hope all of you can recall. This was covered in the combinational logics designing. Now, instead of giving this input, mux input manually, we'll use a 3-bit counter in order to send this parallel data as serial data output on each clock pulse triggering. So if we use this 3-bit counter that will have 8 division starting from 0 up to 7, that means 000 up to 111. In each clock pulse triggering, this value will be changed. Initially, the first clock pulse triggering, it will have 000 value and D0 will be transferred. In the second clock pulse triggering, we will have 001 value in the mux selection input and D1 will be transferred. In this way, this output value Q0, Q1, Q2 value will be increased and one after another data will be sent through this serial data out. This is how we can make a parallel to serial data conversion using counter and mux. There are numerous numbers of applications for counters. Once you know the basic, how to utilize them, then you will be able to design any sort of circuit that requires counting operation. I hope you have understood. Now we conclude here today. Hopefully we'll start with a new topic in the next class. Thank you for your patience hearing. Feel free to contact me if you have any question.